Alright, I'm going to be working through one of the problems you had that was due for homework tomorrow, so if you get a chance to see this, you get a free answer. Simply because I want to test this out and put this up and see if it makes any sense. The problem involves a son and his dad, I believe, playing catch. The boy throws a ball up in the air with some particular initial velocity and at some angle with respect to the ground. And the father over here catches the ball at a height of 2 meters. It's 2.0 meters. And the question asks, at what time, I believe, it's what time is the ball caught? So basically the ball will travel through the air and be caught by the dad here at a height of 2 meters, and it wants to know how long does the ball stay in the air. So it gives us specific information about this angle. Let's just each person's angle is going to be a little bit different, so we'll write down the angle here as being 35 degrees and give it some initial velocity of the magnitude of this initial velocity is going to be, let's say, 20 meters per second. And we want to know how long does this travel in the air. Well, what we don't even, it doesn't even tell us actually how far away the father is or something when he catches the particular ball. It doesn't give us really any other information, as I can recall. The only thing that's really relevant here, it doesn't really matter how far away the father is. The only thing that's particularly relevant is that essentially the boy threw the ball up into the air, and we want to know at what time is the ball at 2 meters. So we can simply figure that out by calculating the. We want to know what the displacement, the time it takes for the displacement of this ball to be 2 meters in the air. So if we have delta y, the displacement of the ball, to be equal to the initial velocity in the y direction times the time that the ball travels, plus 1/2 times the acceleration in the vertical direction times time squared, we should be able to plug in. We have enough information. We know what the initial velocity in the y direction is that we can find, since we know what the angle is plus the magnitude of the initial velocity. We don't know what the time is, but we do know that the acceleration in the vertical direction is equal to gravity. That's the acceleration due to gravity. So we need to be careful about the sign that we associate with that value, and we'll get to that in just a minute. Again, here we have the same time, but that's now squared, and we're also interested in what the displacement is. And we actually have information about that. We want to know at what time is this displacement at 2 meters. And so when we begin to plug in values for this expression, we need to find out what VI, the initial velocity in the vertical direction. And the way that we determine that, we talked about this in class, is simply we want to know the y component of this velocity vector. All right, that's whatever the vertical component of this velocity vector is, and that is equal to the magnitude of that velocity vector times the sine of the angle theta, which in our case is 35 degrees. So we can plug those values in and calculate that out. I'm not sure exactly what that value is. I'm not. Hopefully it's clear that this is actually a kind of a general solution. Actually, to make it the most general, let's not even include the degrees. Let's just leave it as theta, all right? Because we can plug that in and make it pretty obvious what the answer is. So we can plug that value in here. That we have the velocity vector, the magnitude of the velocity vector times sine of the angle theta times time plus 1/2. Now the acceleration here is going to be the same for everyone. We need to make a determination about what we want to be. Since we already specified, actually we already did make a determination about the direction here by labeling this as a positive 2 meters, basically saying that if we assume a y and x-axis here, we write down our positive x-axis being to the right and our positive y-axis being up, that the displacement from the top of the hand here to the ground is a positive 2 meters. And so whatever is higher on the y-axis will be more positives. Hence this is a positive displacement of 2 meters. similarly, because along with that orientation of the y-axis, gravity is always going to be pointing in the downward direction, and because we have the positive y as being up, this requires that our acceleration here is actually negative 9.8 meters per second squared. So we can plug that value in here as well, minus 9.8 meters per second squared. Make sure that's showing up there. Times time squared. So you can plug in your particular values here for VI and sine theta and get some particular number here, which would then give you some value. You have a t squared, t, and another constant. So we have a quadratic equation that we need to solve. The really cool thing, so you solve the quadratic equation, and it will give you two values. You'll get two different time values, and in this case you'll likely get two different time values, okay? T equals something or something else, and I don't want to take the time to calculate them because that's a purely mathematical thing that doesn't require a lot of thinking. You should all be able to do that quite well. The thing I would like to talk about is mathematically, why is that? Even though this is full, this equation right here is ripe with physical significance, because we just pulled this out, right? This is our kinematic equation that we get from our textbook, but it's something we derived from first principles. In the book, we simply assume that we have a constant acceleration, and then we begin to integrate it, right? That's what we did in class, that we integrate this. We started with simply a constant acceleration and integrated with respect to time. And we find the velocity equation for velocity given constant acceleration, and then position given constant acceleration. So this is simply, in mathematical terms, this is simply just a polynomial in t. This kind of looks like this particular curve, that looks like exactly like this curve. And so you can imagine, mathematically speaking, we're left with some, you can imagine here, we just drew some parabola, right? You have lots of parabolas that you had in math class, and it just might as well look like this, just some simple parabola. Sorry about that. And it has interesting information in it. Physically, when we treat this, we have information about where it is here, and it's the origin, and maybe this is where something is being fired. But mathematically, this is all that math really sees. It's just simply this parabola that's described by some function that has the form of like at squared plus bt plus c equal to 0, where a, b, and c have some deep physical significance for the problem that we're doing, but mathematically it doesn't really matter. So what we're asking of this particular equation, we're asking for the solutions in this particular case that coincide with something really interesting. We want to know, we're asking this expression basically by solving for t, when in time does this ball meet the conditions of being at a displacement of 2 meters above the ground? So that's all we're really asking it to do. So here that's kind of what this value c is implying, is when, at what point does c matter, right? At what point does the c value intersect here? It's brushing over a few small details, but essentially that's what we're actually calculating. So that's why we get two different results. It makes physical sense why we get two different results, because we can't ask mathematically precisely what is in that when the ball reaches the dad's hand. All we can ask is, when does this function here that we laid out the equation for, when does that function have a value at 2 meter, have a value of 2 basically above this particular line in space? And that happens at 2 different times. So it should make a great deal of sense that we get 2 different times when we evaluate for t. One time is, so in order to pick one of these times explicitly, sorry, I'm moving my paper around a lot, you need to either choose, the one that makes the most sense. So is the dad catching the ball on the way up, or is he catching it on the way down? And that's what we need to decide. And in this particular case, based on the drawing and what we kind of found, it turns out that the dad is actually catching the ball on the way back down. So it's going to be I use this one because with this one will probably be the smaller value, or the earlier time, and this would be the later one. Okay? So I hope that makes sense, and I hope this loads into Blackboard and works well. See ya.